We've been discussing iterative numerical techniques for getting approximate solutions to elliptic partial differential equations using finite difference methods. We looked at point-by-point methods such as Jacobi, Gauss-Seidel, and SOR, and then in the previous video we looked at the alternating direction implicit method, which we saw has the advantage it can more efficiently move information throughout the domain, which is more elliptic-like. In this and the next couple videos, I want to discuss the multigrid method. This is a very powerful and flexible approach to accelerating those iterative methods. So at its core, it's still an iterative ADI or Gauss-Seidel method, for example, but we're going to wrap around this multigrid framework that can dramatically accelerate the iterative process. Now they're called multigrid methods, as you might guess, because they're going to use multiple grids in the numerical solution. And you'll see how we'll do that, we'll see why we do it, and we'll see how it accelerates these iterative techniques. So first let's start with the motivation, which addresses those questions that I just raised. So we're going to focus on the error. So when we get the numerical solution, that's an approximation to the exact solution. The difference between those two is the error. So that error that arises at any point during the iterative relaxation process, we could express as a Fourier series, as one way to dissect the various features and modes within our error. And what you'll find if you test these iterative techniques that we've been discussing on various types of problems, there's a very consistent behavior as follows. High frequency modes in the error, which have of course very short wavelengths, they tend to experience very fast iterative convergence, whereas low frequency modes, so long, lumbering, large wavelength modes, tend to have very slow iterative convergence properties. So I'll show you examples of this, and then by recognizing this, we can devise a numerical method, the multigrid method, that takes advantage of this property. So we're going to take a really simple example. We're going to take a second order differential equation, d squared u dx squared is equal to 0. The boundary conditions are going to be homogeneous, so u at 0 is 0 and u at 1 is 0. Of course, the solution to that second order differential equation is just a straight line, and if the boundary conditions are both 0 at both ends, the straight line is just u is equal to 0. So the exact solution is u is equal to 0. That's what we're trying to get to. Anytime we plot the current numerical solution, we're actually plotting the error because the exact solution is just 0. So the difference between our numerical solution and the exact solution is the error. So we're going to take this simple one-dimensional problem, we'll subdivide it into capital I equal subintervals, so capital I plus 1 points, as we normally do. And here is using a second order accurate central difference approximation for the difference equation, and then applying the Dirichlet boundary conditions at u1 and u capital I plus 1. And so we're going to solve this for a particular value of capital I. What we're doing here is backwards from what we normally do. Normally we'd have a non-zero, a non-trivial solution, and we would start with a trivial, probably just u is equal to 0 initial guess, and we would iterate until the solution gets close to the correct non-trivial solution. Here it's the opposite. We're going to start with a non-zero initial guess. That'll be the initial error, and then as we iterate, it should iterate towards 0. Just make it easier for us to see how the iterative process is evolving. So I want to illustrate this feature of iterative techniques that I just claimed, and that is that high frequency modes iterate out faster, whereas low frequency modes take longer to iterate out. So let me illustrate that by introducing Fourier modes as our initial guess. So u of x will be sine of k pi x. K here then is a wave number. The smaller the wave number, the smaller the frequency, the larger the wavelength. And the higher the k, the opposite is the case. So ui will be sine of k pi times little I minus 1 over capital I. That's just taking into account our discretization of our x domain into capital I equals subintervals. And then k will determine whether it's a low frequency mode or a high frequency mode, small k or large k. So the claim is that when k is small, where we have long, smooth, therefore low frequency waves, that we will see slower convergence properties, whereas when k is large, we have highly oscillatory, so high frequency waves, we should see faster iterative convergence properties. Let me show that using figures from Briggs. Briggs has an excellent multigrid tutorial. It is the place to start if you want to learn about multigrid, starting from a very basic knowledge of iterative techniques, which we've discussed in previous videos, being able to implement the multigrid method. So I'm going to use those figures here to illustrate these features. So if we were to start with k is equal to 1, so that's just a half sine wave, or 3, so that would be 3 half sine waves, or k is equal to 6, so 6 half sine waves. Those are going to be the initial conditions for solving this simple equation. And again, these are plots of the error because the exact solution is just u is equal to 0. If we were to use Jacobi with, say, capital I is 64, so 64 intervals, 65 points, and we plot the error versus the iteration number. So starting here with our initial guess, and this is after 100 iterations. The error here is normalized, so it always starts at 1. And you'll notice that for k is equal to 1, the iterative convergence is extremely slow. Remember, this is the 1 half sine wave, so it's a low frequency mode, and it's a very slow iterative convergence. Going to k is equal to 3 dramatically improves, and k is equal to 6 further dramatically improves the convergence properties. Exactly the same equation, exactly the same discretization, and exactly the same numerical method. The only difference is the shape, the behavior, the modes that are contained in the original initial guess. And you can see very dramatic differences in the iterative convergence properties. This was for Jacobi. If you do the same thing with Gauss-Seidel, same idea. K is equal to 1, 3, and 6. Now you will notice if I go back and forth, you will notice how much faster Gauss-Seidel is. For example, k is equal to 6 gets down to a rather small value of the normalized error after only 50 iterations, whereas 50 iterations here, it's still rather large. So you can see both the behavior of Jacobi versus Gauss-Seidel as well as the behavior with different initial conditions exhibiting different frequencies. Now let's look at a situation that's more realistic. The more realistic situation will be we have an error, and if you write that as a Fourier series, you're going to have multiple modes. So some of the modes will be high frequency, some of the modes will be low frequency. So let's take an example where we have 3 modes, one with k is equal to 1, one with 6, and one with 32. So we have a low, medium, and high frequency mode all contained in the initial guess. When you apply Jacobi to that with the same number of points as before, you'll see that the error comes down significantly in just the first few iterations, but then it levels off tremendously and slows down the iterative convergence process. What's happening is, and I'll show you this, the high frequency modes are getting beaten down very quickly in those early iterations. Once the high frequency modes have been eliminated, then you only have the low frequency modes which exhibit this very slow convergence process. To show that, here's an example again with Jacobi. K is equal to 3, so 3 half sine waves across the domain. On the left is just 1 iteration. On the right is 10 iterations. So after only 1 iteration with k is equal to 3, you can see there's very little reduction in the error for this low frequency mode. After 10 iterations, you can see it's still only come down by a little bit. So that's very, very slow for this low frequency mode situation. If k is equal to 16, so much higher frequency, you'll notice after just 1 iteration, the error has been reduced quite a bit. After 9 more iterations, so 10 total, you can see it's been reduced significantly. Once again, the only difference is the modes that exist in the original error of the initial guess. It's the only difference. Here's a case where we have 2 modes. K is equal to 2 and 16. So you can see the 2 here is 2 half sine waves, and then 16 is superimposed on top of that. After only 1 iteration, the errors come down relatively significantly. And after 10 iterations, you can see that the high frequency mode, the k is equal to 16 mode, is almost completely gone. Whereas you can see that the k is equal to 2 mode has been very stubborn and has been reduced very, very little. So again, the point is that these iterative techniques are much more effective when they're operating on the high frequency modes in the error than on the low frequency modes. So that brings us to the whole point of the multi-grid method. Why do we use multiple grids? Now this figure, again, it's from Briggs. This is my only criticism of the book. This figure is a little misleading. You'll notice that in the first one, which is on a grid with 12 intervals, that we have a nice smooth curved line through the points. It really should be straight lines between the points to be more accurate to the numerical representation. But that doesn't change the point of what they're showing. Okay, so here's the idea. Here we have a fine grid, okay? 13 points, 12 intervals. If I take out every other point so in this case all the odd number points, then I have 6 intervals, 7 points. The point here is if I take this distribution of the error on this quote-unquote fine grid and convert it to the error on this quote-unquote coarse grid with half as many points, it's going to look very different from the perspective of the iterative method. Here's why. So you notice here I basically have 4 points per lobe, right? Half sine wave. When I take every other point out, I only have 2 for each. So it's a more clunky looking representation of our error. But notice in terms of delta x, in terms of the grid size, the coarse grid version here at the bottom looks higher frequency. From the point of view of, I have more oscillations per grid point here than I do here. So here it's 4 half sine waves over 6 intervals. Here it's 4 half sine waves over 12 intervals. So I'm taking the same error at a particular point in my convergence process, I'm representing it on a coarser grid, and in doing so, the algorithm is going to see what looks like higher frequency modes in the error, and therefore any iteration that I do on that grid will be more effective. That's the basic idea. Now you may have sensed from the way I'm talking about multigrid is it's not so much a method as it is a framework. At the core of multigrid is an iterative technique, Gauss-Seidel or ADI, for example. So we're still using those basic iterative relaxation techniques, but what we're doing is we're wrapping around that this framework, this multigrid framework, which accelerates that iterative process. There's going to be, as you'll see in the next couple of videos, a significant increase in the complexity of these multigrid-based algorithms as compared to their underlying iterative techniques. But the payoff is that multigrid methods are comparable in speed with the fast direct solvers such as FFTs, cyclic reduction, which we can apply to linear elliptic PDEs. The multigrid method is just as fast as those, but they have the added flexibility that we can incorporate these multigrid methods for nonlinear equations. So we can apply this to nonlinear PDEs and get speeds that are on par with FFTs and cyclic reduction, which we sometimes use for linear PDEs. So this is really a remarkable feat in algorithm development. Now there's some other prices to pay, which we'll address in other videos, but in the aggregate, in the net, this is the pièce de résistance. This is the state of the art for solving elliptic partial differential equations.